What if the universe has a speed limit, but hides a loophole inside its own rules? The laws of physics say nothing can outrun light, and yet space itself already does. Distance feels real to us. A meter, a kilometer, a light year. We imagine space as an empty stage, a vast, silent arena where objects move from one place to another. But in physics, distance is not fixed. It is not permanent. It is not even guaranteed. Because space itself does not behave the way our intuition expects. The closest star to Earth after our Sun is Proxima Centauri. It lies just over 4 light-years away. On cosmic scales, that sounds almost nearby, practically next door. But even if you boarded the fastest spacecraft humanity has ever built, the Parker Solar Probe racing through space at more than 400,000 miles per hour, the journey would still take tens of thousands of years. Not because our engines are weak, not because we lack ambition, but because space refuses to cooperate. We can see trillions of galaxies scattered across the observable universe. Their light reaches us from a distant past, traveling for billions of years before touching our eyes. And yet, between us and nearly all of them, there exists an invisible barrier, not a wall made of matter, not a boundary made of energy, but a limit written into the structure of reality itself. For over a century, physics has told us the same thing. Nothing can move through space faster than light. 186,000 miles per second, fast enough to circle Earth multiple times in a single heartbeat. As an object approaches that speed, its energy requirement grows without bound. To reach the speed of light would require infinite energy. To exceed it would cause the mathematics of physics to collapse entirely. This is not a technological problem. It is not something better engines can solve. It is built into space-time itself. So we assume the problem is speed, that if we could only build faster ships, stronger fuels, more powerful drives, then the universe would finally open its doors. But physics suggests something far stranger. What if the problem was never speed at all? What if the mistake lies in how we think about travel? Because Einstein revealed something unsettling about the universe. Space is not a passive backdrop where events unfold. It is not empty. It is not rigid. It bends. It stretches. It responds. Gravity is not an invisible force pulling objects together. It is curved space telling matter how to move. And if space can bend, then it can also change. At this very moment, there are galaxies at the edge of the observable universe moving away from us faster than the speed of light. Not because they are breaking any laws, not because they are racing through space at impossible velocities, but because the space between us and them is expanding. Imagine 2 dots painted on a massive rubber sheet. The dots themselves do not move, but as the sheet stretches, the distance between them grows. Neither dot violates any speed limit. The surface beneath them simply changes. That is what the universe is doing. Space expands, and it can do so at any speed. For every few million light-years of distance, the expansion adds a little more velocity. Over vast cosmic scales, that addition becomes enormous, large enough to surpass the speed of light without breaking physics at all. And this behavior is not rare. In the first fraction of a second after the Big Bang, the universe underwent something extraordinary, a period known as cosmic inflation. In less time than light takes to cross the width of an atom, space expanded by a factor so immense It defies comprehension. The entire observable universe grew from smaller than a grain of sand to larger than a galaxy almost instantly. During inflation, space expanded far faster than light could ever travel through it. The universe broke its own speed limit on day one, and it has been doing so, quietly, ever since. Which raises a disturbing question. If space itself can expand and contract faster than light, and if this behavior is already allowed by the laws of physics, then why couldn't it happen locally? In 1994, a physicist named Miguel Alcubierre noticed this loophole. Alcubierre was deeply familiar with Einstein's general relativity, the same equations that describe black holes, gravitational waves, and the subtle timing corrections required for GPS satellites to function correctly. Those equations do not forbid faster than light expansion. They simply forbid objects from moving through space faster than light. So Alcubierre asked a different question. What if a spacecraft never moved through space at all? What if space itself moved instead? He sat down with Einstein's field equations and searched for a solution. Not an invention, not a machine, but a pattern of space-time curvature that physics already allowed. And remarkably, he found one. In his solution, space in front of a spacecraft contracts. Distances shrink. 10 light years become 1. Behind the spacecraft, space expands. 1 light year becomes 10. The ship itself sits calmly inside a bubble of flat, normal space-time, untouched by extreme forces, not accelerating, not breaking any physical laws. The bubble moves. From the outside, the ship appears to travel faster than light. From the inside, it is not moving at all. It is being carried. Like a surfer riding a wave across the ocean, the surfboard is not racing through the water faster than swimming would allow. The wave beneath it is moving a traveling distortion in the medium itself. The warp drive works the same way. Not motion through space, but motion of space. Alcubierre published his findings in a peer-reviewed physics journal. The title alone shocked the scientific community. Faster than light travel derived directly from Einstein's equations. Some physicists searched for flaws. Others searched for improvements, because the mathematics was valid, but the consequences were unsettling. There was a catch. To create such extreme distortions of space-time, the warp bubble would require something called negative energy, not ordinary matter, not anything we have ever observed. Negative energy would behave opposite to everything we know. It would repel rather than attract. Gravity that pushes instead of pulls. Matter that falls upward instead of down. We have never detected it, never produced it, never confirmed that it can exist in usable quantities. When Alcubierre first calculated how much would be required, the result was staggering. Enough negative energy to equal the mass of Jupiter converted entirely into something unknown, not impractical, absurd. But years later, physicists revisited the mathematics. In 2012, NASA researcher Harold White discovered that by altering the geometry of the warp bubble, adjusting its thickness and shape, the energy requirement dropped dramatically. From the mass of a planet to something closer to the mass of a small car. Still exotic, still hypothetical, still beyond our current abilities. But the scale changed by trillions upon trillions, not because technology improved, but because understanding did. Whether warp drives will ever exist remains unknown. Perhaps negative energy is impossible. Perhaps nature will refuse at the final step. But one thing is now clear. The universe does not limit us because we are slow. It limits us because we misunderstand motion. Because sometimes the fastest journey is not about moving faster. It is about moving differently. At one point, warp drive wasn't just difficult. It was impossible. Completely outside the boundaries of physics. Something that belonged entirely to science fiction, entertaining, imaginative, but fundamentally unreal. And now, it isn't. Today, warp drive sits in a strange new place. Not achievable, not practical, not something we could build tomorrow or even next century, but no longer forbidden, and that distinction matters. Because the problem no longer seems to be that warp drive cannot work. The problem is that we don't yet know how to obtain the ingredients. Maybe one day we'll learn how. Or maybe those ingredients simply don't exist at all, and warp drives will remain forever trapped inside equations and thought experiments. But something important has already changed. We found the loophole. For more than 100 years, the cosmic speed limit felt absolute, unquestionable, a hard wall at the edge of reality. Then Alcubierre showed us the fine print. Yes, the universe has a speed limit, but only for objects moving through space. Space itself plays by different rules. Space can stretch. Space can compress. Space can move however it wants. And if we ever become clever enough, if we learn how to influence space the same way the universe does naturally during cosmic expansion, then that loophole might become usable. The cage still exists, but now we know it has a door. We can see it clearly. We understand exactly how it opens. All that remains is the final question. Is the handle real or imaginary? To understand what that means, imagine standing at the edge of the ocean. Waves roll steadily toward the shore. Water rises and falls in slow, rhythmic motion. Now imagine you're sitting on a surfboard, waiting. A wave approaches from behind. The water beneath you lifts upward. Suddenly, you begin moving forward, not because you're paddling, not because you're swimming, but because the wave itself is carrying you. You aren't fighting the ocean. You're letting it move you. That's the basic idea behind warp drive. You don't push through space. You create a wave in space itself and ride it. But that raises a deeper question. How do you make a wave in something you can't touch? How do you bend space? The answer lies in gravity, or more precisely, in mass and energy bending space-time. Picture a trampoline stretched perfectly flat. Now place a heavy bowling ball in the center. The fabric sags downward, creating a curved depression. Roll a marble nearby, and it curves inward, not because the bowling ball pulls it directly, but because the surface beneath it is no longer flat. That's gravity. Mass bends space. Objects simply follow the curves. Earth creates a small dip. We live inside it. The sun creates a much deeper one. Planets orbit within that curvature like marbles circling a bowl. Black holes create curves so steep that nothing can climb back out, not even light. All of this happens passively. Mass sits in place. Space bends. Objects respond. But warp drive asks a more radical question. What if space didn't just respond passively? What if we could push and pull on it deliberately? What if we could shape curvature on demand without relying on massive planets or stars? That's what exotic matter would allow. Normal matter creates attractive curves, dips, and valleys that pull things inward. Exotic matter would do the opposite. It would create hills and ridges in space-time regions that repel instead of attract. The warp drive depends on arranging those repulsive and attractive effects into a very precise pattern, not a static distortion. A moving one? Ahead of the spacecraft, space is compressed, squeezed together like an accordion. Behind it, space is stretched outward, pulled thin like taffy. Together, these distortions form a traveling wave, and the ship rides that wave. In practical terms, exotic matter would form a shell around the spacecraft, like a hollow ring or donut, completely surrounding it. Inside that shell, where the ship actually sits, space remains perfectly normal, flat, calm, undisturbed. You could walk the corridors, drink coffee, run experiments. Everything behaves exactly as it would far from any star. Time flows normally. Physics behaves normally. Nothing strange happens inside. Outside the shell, however, space-time is violently curved. Ahead of the ship, distances shrink. A ruler that normally measures 1 foot might now span 10 feet of real distance. Behind the ship, distances stretch. That same ruler might cover only an inch. Space itself is being reshaped. And here's the remarkable part. This bubble doesn't sit still. The compressed region ahead and the expanded region behind form a slope like a hill made of space-time, and the bubble slides along that slope. The ship moves because the geometry beneath it moves. From the outside, the bubble appears to race through space, potentially far faster than light. From the inside, nothing moves at all, because the bubble is not an object traveling through space. It is a pattern, a distortion propagating through space-time itself. And patterns don't obey speed limits. Think of ripples spreading across a pond. When you drop a stone, the water molecules don't travel across the pond. They mostly bob up and down in place. Yet the ripple moves outward. Energy moves. Information moves. The pattern travels, even though the water itself remains largely where it started. A warp bubble behaves the same way. Space isn't flowing forward, but a curvature pattern is moving through it. And the ship, resting safely in the calm center, is carried along. The speed depends entirely on how extreme the distortion is. Compress space ahead by a factor of 1,000. Expand space behind by the same amount. Now, 1,000 light-years of normal distance effectively becomes 1 light-year of travel. In theory, there is no upper limit. Want to cross the Milky Way 100,000 light-years in a single week? The mathematics allows it. That would require the warp bubble to move roughly 5 million times faster than light. Not because the ship moves that fast, because space does. Of course, we have no exotic matter, not a gram, and certainly not vast quantities arranged in perfect geometric precision. But on paper, within Einstein's equations, arbitrarily high speeds are permitted. And inside the ship, something remarkable happens. Time behaves normally. Cross 100,000 light-years in 7 days, and you age 7 days. Your clock advances 1 week. This is profoundly different from conventional near-light speed travel. If you accelerated a ship to 99% of light speed using ordinary rockets, time dilation would dominate. A year for you might mean many years passing back on Earth. But inside a warp bubble, there is no such penalty. You are not racing through space-time. You are sitting calmly while space-time rearranges itself around you. As your ship approaches light speed, say 99.99%, time begins to separate dramatically. While only a single year passes for you, 70 years pass back on Earth. Push it further, and the gap becomes extreme. 1 year for you could mean 70 years at home. You could depart on a long mission, experience only a handful of years, then return to discover that everyone you ever knew is gone, and civilization itself has evolved into something unrecognizable. A warp drive changes that entirely. Inside a warp bubble, time flows at the same rate for you and for Earth. You leave on Monday, arrive on Friday, and it's Friday everywhere. No time dilation. No returning to a future that has raced far ahead without you. You remain synchronized with your society. For interstellar travel, that difference is enormous. With relativistic travel, you slowly drift out of history. With warp travel, you don't. But the problems begin immediately. The first issue is what you would actually see. Light moving through warped space doesn't behave normally. At the boundary of the warp bubble, where ordinary space transitions into intensely curved space-time light rays, bend violently. Looking through a window, the stars would not appear as familiar points scattered across the sky. Stars in front of you would collapse into a single, blinding blue concentration. Not because you're moving toward them inside the bubble, you're essentially stationary, but because space ahead is compressed. Light traveling through compressed space has its wavelength shortened. The blue shift comes from geometry, not velocity. Behind you, the opposite occurs. Space is stretched. Light waves elongate. Stars smear into deep red streaks. Red shifted by expansion itself. The view would be breathtaking and completely unusable. Visual navigation would be impossible. The bubble boundary would distort images beyond recognition, like peering through an unimaginably powerful gravitational lens that bends reality into abstract shapes. Even more serious is isolation. Warp travel fundamentally cuts you off from the rest of the universe. Your bubble moves faster than light relative to the surrounding space. For any signal from outside to reach you, it would need to overtake the bubble, but nothing can travel faster than light. Not radio waves, not lasers, not anything. The same is true in reverse. Signals you transmit cannot escape. They fall behind as the bubble outruns them. No communication in, no communication out, no updates, no warnings, no way to ask for help. Once the bubble forms, you are alone. That means the entire journey must be planned in advance. You must calculate exactly where your destination star will be, accounting for its motion through the galaxy during your travel time. The trajectory must be perfect from the start. After launch, there is no steering, no mid-course correction, no adjustment of any kind. If your calculations are slightly wrong, if the star has drifted more than expected, or an unseen object lies in your path, you won't know until you arrive. You could emerge light years from your intended destination. You could exit inside the outer atmosphere of a star. You could appear directly in the path of an asteroid. You are flying blind, sealed inside a bubble of distorted space, trusting mathematics alone. And space is not empty. Between stars exists the interstellar medium, thin, but not non-existent. On average, there are roughly 1 hydrogen atom per cubic centimeter. That sounds trivial, until you multiply it across light years. On a 4 light-year journey to Proxima Centauri, your warp bubble would sweep through trillions upon trillions of hydrogen atoms. Those atoms cannot enter the bubble. To do so, they would need to exceed the speed of light. Instead, they accumulate. They pile up along the front edge of the bubble like snow building against a plow. When you finally arrive and shut down the warp field, all that collected matter is released at once. Hydrogen atoms, dust particles, cosmic rays, everything compressed during the trip erupts forward in a focused blast. Physicists have calculated the result. For a 4-light-year journey, roughly 700 grams of hydrogen would accumulate. When released, that mass becomes a particle beam with energy comparable to a gamma-ray burst among the most violent events in the universe. Aim that beam at a planet and the consequences are catastrophic. The atmosphere ionizes. The surface is flooded with lethal radiation. Any complex life would be wiped out within hours. Your arrival is not gentle. It is a weapon accidental, but devastating. Because of this, you cannot exit warp near inhabited worlds. You would need to emerge far away, perhaps several times the Earth-Sun distance, allowing the particle blast to dissipate harmlessly. Only then could you approach using conventional propulsion. That adds time. Maybe days of normal travel after the warp journey, still unimaginably faster than traditional interstellar flight, but the complications keep growing. Then there's the stability problem. A warp bubble depends on an exquisitely precise shell of exotic matter arranged in perfect geometry. Maintaining that structure for hours or days would require control systems of extreme accuracy. Minor fluctuations might be correctable. Major ones could destabilize the entire bubble. If the bubble collapses mid-flight, space snaps violently back to normal. The compressed region ahead expands explosively. The stretched region behind contracts. The ship would be thrown by rapidly shifting space-time itself. Tidal forces could rip it apart. Even if the structure somehow held, the crew would experience acceleration strong enough to kill them instantly. And the energy released when the bubble collapses is staggering. Calculations suggest localized intensities rivaling a supernova, enormous radiation bursts, gravitational waves rippling outward. Observers light years away would see a sudden flash in the darkness. Warp travel, if achievable, would be extraordinarily dangerous. You cannot communicate. You cannot change course. You cannot recover from major failure. One mistake, and the journey ends. And yet, if every one of these problems could be solved, the payoff would be historic. Light years could be crossed in days rather than thousands of years. Other star systems could be reached within a single human lifetime. Galactic exploration would no longer require generations of travelers. It could be done by individuals. Mathematically, the idea works. Einstein's equations allow it. We understand how the bubble would form, how space would curve, how the ship would ride the distortion like a wave. What we lack is the impossible ingredient. About 700 kilograms of exotic matter, something humanity has never observed, never created, and never detected anywhere in the universe. To grasp how severe this problem is, imagine being asked to build a house, except the blueprints demand bricks made of solid light, not glowing bricks, not illuminated bricks, actual light, hardened into stackable material. You would immediately say it cannot be done. Light is not a building material. It does not behave that way. That is exotic matter. Everything you have ever touched has positive mass. Your body, this planet, the Sunday distant galaxies, all possess normal mass, and normal mass produces gravity that attracts. Drop a ball, it falls downward. The moon orbits Earth. Earth orbits the Sunday. Galaxies pull on galaxies. Attraction is universal. Gravity always pulls inward. Every massive object curves space in a way that draws other objects closer. This is so fundamental that imagining an alternative feels almost impossible. Exotic matter would reverse all of it. It would possess negative mass and negative energy. Instead of forming a gravitational well, it would create a gravitational hill. Instead of pulling objects inward, it would push them away. Place a ball near negative mass, and it would accelerate upward. Place negative mass near Earth, and Earth would move away from it. Repulsion instead of attraction. And this has never been observed anywhere. We have studied neutron stars, where matter is crushed to nuclear densities. We have observed black holes, where space-time itself is violently distorted. We have examined the early universe, moments after the Big Bang, when energies exceeded anything that has existed since. And in every case, without exception, we find only positive mass creating ordinary, attractive gravity. No negative mass, no exotic matter, no anti-gravity. And without it, warp drive remains an idea permitted by mathematics, but forbidden by reality. Never repulsion, never anti-gravity, never negative mass. And yet the warp drive equations demand exactly that, not as a bonus feature, not as an upgrade, but as an absolute requirement. There is no way to sculpt space-time into the needed shape using only ordinary positive mass. You cannot compress space in front of a ship and expand it behind using normal matter alone. The geometry simply won't form. The equations insist on negative energy density, a shell of it wrapped around the vessel. When Miguel Alcubierre first derived his solution, the numbers were staggering. His original model required an amount of exotic matter equivalent to the mass of Jupiter, the largest planet in our solar system, roughly 300 times the mass of Earth, converted entirely into something we aren't even sure exists. Jupiter alone outweighs all the other planets combined. Sacrificing an entire gas giant just to move a single spacecraft is beyond absurd. Even if such a transformation were possible, which it isn't, interstellar travel would mean dismantling planetary systems one trip at a time. In 2012, physicist Harold White proposed an optimized version. By reshaping the warp bubble and adjusting its thickness, he reduced the energy requirement dramatically down to about 700 kilograms, roughly the mass of a small car. Still impossible, but psychologically transformative. Jupiter's mass feels fundamentally unreachable. 700 kilograms feels like something a far future civilization might at least imagine handling if exotic matter exists at all. So what do we actually know? Quantum mechanics tells us that empty space is not truly empty. The vacuum seethes with activity. Tiny particle pairs constantly appear and vanish. An electron and its antimatter counterpart briefly pop into existence, then annihilate almost instantly. This happens everywhere, all the time, at scales far too small to observe directly. These quantum fluctuations normally produce positive vacuum energy, but under very specific conditions, physics allows something strange, tiny pockets where the energy becomes negative. The Casimir effect demonstrates this. Place two flat metal plates in a vacuum, separated by an unimaginably small distance, just a few nanometers apart, about 100,000th the width of a human hair. That narrow gap restricts which quantum fluctuations can exist between the plates. Only certain wavelengths are allowed inside, while outside the plates, all wavelengths continue freely. This imbalance matters. Fewer fluctuations exist between the plates than outside. The energy density inside the gap becomes slightly negative relative to the surrounding vacuum. The result is a real, measurable force pushing the plates together. Hendrik Casimir predicted this in 1948 using quantum theory alone. In the 1990s, experiments confirmed it with remarkable precision. So negative energy is real. But here's the critical limitation. The Casimir effect produces absurdly tiny amounts of negative energy confined to absurdly tiny regions, lasting for absurdly short times. The separation must be nanometers. The force is smaller than the weight of a grain of sand. The measurable area is smaller than your fingernail. Warp drive requires something entirely different. It needs roughly 700 kilograms of exotic matter distributed across a shell several meters wide, sustained continuously for hours or days. Compare the scales. Casimir effect, nanometer gaps, billionths of a Newton, microscopic surface areas, warp drive, meter-scale structures, kilogram-level energy densities, stable operation over long durations. The gap is enormous, roughly 30 orders of magnitude in size and 40 orders of magnitude in energy. That's like proving you can light a match and concluding you can therefore melt continents. So the question isn't whether negative energy exists. We already know it does. The question is whether it can be amplified to macroscopic scales. And quantum physics may say no. There's a concept known as the quantum interest conjecture. It suggests that negative energy can exist only temporarily and only if it is overcompensated later by positive energy. Nature allows you to borrow negative energy, but demands repayment with interest. Imagine a bank that lets your account go negative briefly, but for every dollar you borrow, you must eventually repay too. You can dip below zero, but you cannot stay there. And the deeper you go negative, the more violently the system pushes back. If this principle is correct, and several quantum theorems support it, then sustained, large-scale exotic matter is impossible. You may create fleeting microscopic pockets, like the Casimir effect, but you cannot maintain the continuous negative energy distributions a warp drive requires. Some physicists suspect this is not a technological limitation, but a fundamental safeguard built into reality itself. Not something we haven't figured out yet, something the universe simply does not allow. Then there's dark energy. This mysterious substance makes up roughly 70% of the universe and drives cosmic expansion. Galaxies are accelerating away from each other because of it. Dark energy behaves as though it has negative pressure, pushing space apart instead of pulling it together. Because of that, some researchers wonder whether dark energy might be related to exotic matter. But we don't understand dark energy at all. We know it exists only because we see its effects. We have no idea what it actually is. And it's spread incredibly thin, uniformly distributed across all of space at an extremely low density. Hoping dark energy will solve the warp drive problem is not a plan. It's a wish. Other possibilities are often mentioned. Perhaps string theory allows exotic matter under special conditions. Perhaps quantum gravity effects at ultra-small scales could generate it. Perhaps entirely unknown mechanisms exist. But string theory remains unproven. We don't even know if it describes reality. Quantum gravity is still unsolved. We lack a complete theory. We are speculating about speculative physics layered on top of unsolved physics. And then comes the sobering observation. If exotic matter could exist naturally, we would expect to see it somewhere. The universe has had 13.8 billion years to create it. Neutron stars compress matter beyond nuclear density. If extreme compression could produce exotic matter, neutron stars should contain it. We see none. Black holes generate the strongest gravitational fields known. If extreme curvature could create exotic matter, it should appear near them. We see no sign. The early universe reached energy densities far beyond anything that has existed since. If exotic matter could form under extreme conditions, it should have appeared then. Cosmological observations show no trace of it influencing cosmic evolution. Everywhere we look, every environment, every era, we find the same thing: positive mass, attractive gravity, never repulsion, never anti-gravity, never exotic matter. That absence is meaningful. It suggests that exotic matter may exist only as a fleeting quantum curiosity, not as a substance you can collect, store, or engineer. The Alcubierre warp drive may be like a mathematical perpetual motion machine, internally consistent, beautiful, perfectly valid on paper, but unrealizable because the universe refuses to provide the ingredients. The equations are not wrong. The universe may simply say no. Perhaps future physics will reveal a pathway we cannot imagine today. Perhaps a breakthrough will show how to create, stabilize, and control exotic matter. Or perhaps we will eventually prove that quantum mechanics forbids it absolutely, that the door we discovered is painted on the wall, flawless in detail, but with no opening behind it. We won't know until deeper questions are answered, until quantum gravity is solved, until we understand what space and energy truly are. That could take decades. It could take centuries. It might never happen. For now, 700 kilograms of impossible material stand between humanity and the stars. The door is visible. We can describe it. We can calculate exactly how it would open, but the handle may be made of imagination. Still, let's dream for a moment. Assume we solved it. Someone figured out how to create exotic matter, stabilize it, control it. The first Alcubierre drive is built. You stand on the bridge of humanity's first warp-capable spacecraft. Engineers complete their final checks. Your destination is programmed. Proxima Centauri, 4.2 light-years away. At conventional speeds, 70,000 years. With warp travel, if the equations are right, perhaps 36 hours. The exotic matter generators come online. You feel nothing. No vibration, no acceleration, no rumble. Only a subtle change in the light beyond the windows. Stars ahead begin to compress. Their light shifts toward blue, not because you're racing toward them, but because space itself is contracting in that direction. Behind you, stars smear and redden as space stretches outward. The colors aren't changing due to motion. They're changing because geometry itself is being reshaped. Then the bubble finishes forming. You now exist inside a 10-meter sphere of perfectly ordinary space. Around you lies a thin shell of exotic matter, sculpting an impossible curvature in the space beyond. The boundary between your calm interior and the violently warped exterior is razor sharp, maintained with nanometer-level precision by constantly adjusted exotic matter distributions. And then you're moving, except you're not. You stand up and feel normal gravity, 1g, generated by rotating sections of the ship. You walk normally, pour water from a cup, and it flows exactly as it should. Drop a pen, and it falls at the expected rate. Inside the bubble, physics behaves completely normally. Locally, you are sitting in flat, empty space. Your clock ticks normally. Your body ages normally. Time flows as it always has. But outside is something else entirely. To any external observer, if such an observer could exist, your ship would appear to shimmer for a brief moment. Then it would seem to vanish as the warp bubble detaches from the surrounding space. The bubble would shoot away faster than light itself could follow, leaving emptiness behind. You feel none of that. Inside, you're simply sitting there reading a book, drinking coffee, waiting. At this speed, the journey to Proxima Centauri takes roughly a day and a half, about 36 hours. During that entire time, you are completely cut off from the universe. Think about what that means. Right now, Earth exists. People are living their lives. Cities are awake. Conversations are happening. But none of that can reach you. Radio signals can't catch up. Light can't catch up. Information itself cannot overtake your faster-than-light bubble, and you can't send anything back. Any transmission you broadcast falls behind instantly, unable to keep pace. You exist inside a pocket of causality, a region of space-time temporarily disconnected from the rest of reality. It's like sitting inside a perfectly soundproof room during an earthquake. Inside, everything is calm and silent. Outside, the building may be collapsing, and you would never know, except here, you can't open the door. Not until you arrive. Your instruments show almost nothing beyond the bubble. The extreme curvature at the boundary bends incoming light so violently that external images are warped beyond recognition. You might see compressed clusters of blue ahead, smeared red streaks behind, but nothing usable. Navigation by sight is impossible. Before departure, you programmed the destination. You calculated where Proxima Centauri would be 36 hours in the future, accounting for its motion through space. You set the trajectory. Now you're committed. If your math was off, if Proxima's movement differed slightly, if an unseen companion star lies along the route, if a rogue planet drifts through your path, you won't know until arrival. You are flying blind through interstellar space at millions of times the speed of light, trusting calculations made days earlier. And you are not traveling through emptiness. The interstellar medium is real. Hydrogen atoms, cosmic rays, dust grains, on average, about 1 hydrogen atom per cubic centimeter. That sounds insignificant until you cross 4 light years. 4 light years is roughly 40 trillion kilometers. Your bubble's cross-section might be 100 meters wide. Across that distance and volume, you encounter roughly a billion hydrogen atoms. Those atoms cannot enter the bubble. To do so, they would need to move faster than light to match your bubble's motion. They can't. So they accumulate. They pile up along the forward boundary, building layer upon layer like snow collecting on the blade of a plow. Over the 36-hour journey, roughly 700 grams of hydrogen collects at the front edge, along with cosmic rays, dust, and any larger particles you happen to intercept. 700 grams doesn't sound dangerous, but it isn't just sitting there. It's compressed by the bubble boundary. energized by its interaction with warped spacetime. When you arrive and collapse the bubble, all of that stored matter is released at once in a tightly focused forward blast. Picture this. You're driving through a snowstorm. Snow builds up on your windshield. Now imagine you're moving at 1,000,000 miles per hour, and the snow is being compressed into solid ice by unimaginable pressure. When you stop, that compressed mass explodes forward with all the energy it accumulated during motion. Except here, it isn't snow. It's hydrogen nuclei and cosmic radiation. And instead of air pressure, it's space-time curvature. The resulting energy release is comparable to a gamma-ray burst. Gamma-ray bursts are among the most powerful explosions in the universe after the Big Bang. For a few seconds, they can outshine entire galaxies. They release as much energy as the sun will emit over its entire 10 billion year lifetime. Your warp arrival creates a miniature version focused forward. Aim that at a planet, and everything on the facing side dies. The atmosphere ionizes. Radiation floods the surface. Any living organism receives lethal doses within moments. The ground itself may briefly glow from the deposited energy, so you cannot arrive close. You cannot exit warp near planets orbiting Proxima Centauri. You would annihilate anything living there before ever making contact. Instead, you must emerge far away, perhaps 10 times the Earth-Sun distance out, far enough that the particle beam disperses harmlessly into space. Only then can you use conventional rockets for final approach. That adds time, maybe another day of normal travel, still vastly faster than 70,000 years. But your 36-hour journey has now become 60 hours once safety is included. And that's assuming everything goes perfectly. What if it doesn't? What if the exotic matter generators fluctuate? What if power levels drift? What if the bubble geometry destabilizes? The warp shell depends on exact distributions of exotic matter, precise densities, perfect spatial patterns, tightly controlled energy states. Control systems constantly perform microscopic adjustments to keep the bubble stable. But no system is flawless. A generator fails. A software error occurs. A power spike hits. The bubble begins to oscillate. The boundary between flat interior space and warped exterior space starts fluctuating. Space itself begins to convulse, contracting, expanding, vibrating violently. Inside, you feel it. Tidal forces appear. The front of the ship experiences different curvature than the back. You are stretched and compressed as space-time ripples around you. If the disturbance is mild, automated systems might correct it, stabilize the field, restore equilibrium. If it's severe, the bubble collapses. Space snaps back to normal geometry in an instant. The compressed region ahead explodes outward. The expanded region behind slams inward. The ship is whipped violently as space-time rebounds. Structural members fail. Metal shrieks. The crew experiences acceleration so extreme they are killed, instantly crushed into the walls before nerves can even register pain. Then comes the energy release. All that warped space-time suddenly relaxing produces an enormous burst. Gravitational waves surge outward. Radiation floods the region. From light years away, it would look like a supernova detonated in empty space. Nothing survives. One moment, you're reading quietly in your cabin. The next moment, space-time itself tears you apart. There is no warning, no alarm, no time to react. You cannot detect the danger in advance. You cannot receive external alerts. You cannot escape. Once the journey begins, you are sealed inside, relying on perfect engineering and luck. But imagine you make it. 36 hours pass. Your instruments indicate the initiation of bubble collapse. Exotic matter generators begin powering down. The warped space around you slowly relaxes. The compressed blue stars ahead drift back to normal color. The red-smeared stars behind return to familiar points of light. Distortions fade. The outside universe sharpens into clarity. And there it is, Proxima Centauri, a small, dim red dwarf star, about 1/8 the mass of our Sunday. Tiny compared to the sun you left behind, yet you're here. You made it. The warp bubble collapses completely. At the front edge of your former path, the accumulated particles are released in a narrow, concentrated beam. They surge forward at nearly the speed of light, racing away from your ship. Your instruments track the burst as it fades into deep space, far from any planets. No damage done. You're back in ordinary space now, 4.2 light-years from Earth, just 36 hours after departure. Light from the moment you left Earth won't reach Proxima for another 4 years. You arrived before your own farewell ever could. You stand at the viewport and look back. Earth is out there somewhere, a faint yellow star, lost among thousands, indistinguishable to the naked eye. Your home, your family, everyone you've ever known. 4 light-years away, a distance humanity once believed impossible to cross within a lifetime, yet you crossed it in a day and a half. Here's the strange part. Back on Earth, only 36 hours have passed. Exactly the same as for you. Your clocks are synchronized. You left Tuesday morning. It's now Wednesday night, for you and for them. That's what makes this different from relativistic travel. At 99% the speed of light, time dilation would tear you away from humanity. You might experience a few years while decades or centuries passed on Earth. You'd return to a world where everyone you knew was gone. Warp drive erases that. Time flows identically everywhere. You age 36 hours. Earth ages 36 hours. When you return another 36-hour journey, you'll have been gone 3 days. Just 3 days. No temporal exile. No future shock. No lost civilization. You remain part of humanity. That's the dream. That's what warp drive truly offers, not merely faster travel, but connected travel. The ability to explore the galaxy without abandoning your species in time. You look out toward Proxima Centauri and understand what you've done. You are the first human to enter another star system, the first to see another sun up close, the first to cross interstellar space within a human lifetime. You are farther from home than anyone has ever been, yet you are not lost, not displaced, not cut off. You're simply somewhere else, and you can go back whenever you choose. That's the beauty of it. That's what separates warp drive from every other interstellar concept humanity has imagined. But it comes at a cost. It requires exotic matter. It demands materials that may not exist. It relies on physics we don't yet know how to control. And even if we build it, it may still be too dangerous to use. You reached Proxima, but your arrival nearly destroyed whatever might have existed here. Your journey was a gamble with your life. Your technology rests on impossible ingredients. The door opened. You walked through. But the price may be unbearable. You settle into orbit around Proxima Centauri b, the potentially habitable planet circling the nearest star. Sensors activate. Instruments begin scanning. The readings are promising. An atmosphere, water vapor signatures, possible biological markers. This could be it. Another living world. The first time humanity encounters life that evolved independently of Earth. Then something changes. Atmospheric data begins shifting rapidly. Upper layer ionization spikes. Radiation levels surge. Energy deposition patterns spread across the hemisphere facing your ship. You recheck the instruments. The radiation is coming from behind you, from the direction you arrived, from the path your warp bubble traveled. And suddenly you understand. You thought you had emerged far enough away. 10 times the Earth-Sun distance felt safe. The particle beam from bubble collapse should have dispersed harmlessly into space. But you didn't account for the planet's exact position. You didn't realize Proxima b lay directly within the beam's path, even at that distance. Your calculations were off by a fraction of a degree. Meaningless for most navigation. Catastrophic here. The particle beam, 700 grams of hydrogen, and cosmic radiation accelerated to near light speed, struck the planet's atmosphere head-on. The upper atmosphere ionized instantly. Molecules were torn apart. A column of superheated plasma formed where the beam impacted. Shock waves rippled outward. On the surface below, anything within the strike zone was flooded with lethal radiation. Not just surface sterilization. The beam penetrated deep. Ozone layers collapsed. Protective barriers against stellar ultraviolet radiation were shredded. If life existed, their complex organisms, ecosystems, perhaps even something approaching intelligence. It's dying now. Radiation poisoning. DNA fragmented. Cells unable to repair the damage. Your arrival just killed a world. Not deliberately. You took precautions. You emerged at what seemed like a safe distance. But the universe doesn't care about intention. Warp bubble collapse produces particle beams. Those beams carry enormous energy. And if anything lies in their path, it gets hit. This is one of warp drive's darkest implications. Every journey creates a potential weapon. Every arrival releases stored energy, and you can't always predict where that energy will go. You can try to reduce the risk, emerge farther away, maybe 100 times Earth's orbital distance instead of 10. Travel only through low-density regions of space to accumulate fewer particles. Design bubble geometries meant to capture matter during collapse. But every fix adds new problems. Greater emergence distance means longer conventional travel times. Avoiding dense regions restricts navigation routes. Capturing accumulated particles may be impossible due to causality limits. And even if the accidental weapon problem were solved, there's the deliberate one. Military strategists would see it immediately. A warp-capable ship can arrive anywhere and release a directed energy blast simply by shutting down its drive. No missiles required. No warheads needed. The warp engine itself becomes the weapon, and it could be made worse. Route a ship through a dense nebula before arrival. Accumulate kilograms of matter instead of grams. Convert that into a focused particle beam capable of cracking continents. Consider the Orion Nebula thousands of times denser than average interstellar space. A 4-light-year journey through it could accumulate 10 kilograms of material. Released at near light speed, that's civilization-level destruction. Cities vaporized. Ecosystems erased. A single warp vessel could surpass the destructive power of entire nuclear arsenals, and there would be almost no defense. The ship arrives faster than light. By the time it's detected, the beam has already been released. No warning, no evacuation, no countermeasures, just sudden devastation. This creates ethical and political problems unlike anything humanity has faced. Even if we solve exotic matter, even if we build warp drives, should we use them? Can we approach inhabited worlds safely? Can we explore responsibly? Can we trust ourselves with technology that turns every spacecraft into a potential superweapon? History offers little reassurance. Every powerful tool humanity has invented has been weaponized. Nuclear fission could power cities or erase them. Rockets could launch satellites or deliver warheads. The internet could unite humanity or enable mass surveillance. Warp drive would be no different. Built for exploration, used for war. Treaties might help. The Outer Space Treaty of 1967 bans weapons of mass destruction in orbit and forbids military use of celestial bodies. We could extend such rules, banning warp emergence near inhabited systems, enforcing minimum distances, prohibiting military usage. But enforcement across interstellar distances is impossible. A ship could violate protocols light years away. Earth wouldn't know for years. By the time information arrived, it would already be too late. You cannot police a galaxy where information moves at light speed, but violations occur faster. And there's another issue, subtler, but perhaps even more significant. Warp bubbles generate gravitational waves. Dragging that much distorted space-time through the universe produces ripples in geometry itself, not gentle waves like orbiting black holes, but intense localized disturbances from rapidly moving curvature. These waves propagate outward at light speed. They are detectable. Our detectors on Earth, LIGO and Virgo, can sense black hole mergers billions of light years away. A warp bubble passing through nearby space would produce signals orders of magnitude stronger. Warp travel cannot be hidden. Any civilization with gravitational wave detectors would see you coming hours before arrival. They could calculate your trajectory, know your destination. For peaceful exploration, that's acceptable. For military use, it's disastrous. You cannot approach secretly. Any civilization advanced enough to be interesting would almost certainly detect you. But there's another side to this. Gravitational waves could be used intentionally. By modulating warp bubble geometry, information could be encoded into those waves. The signals would still travel at light speed, not faster, but they would pass through matter almost unhindered. Nearly nothing blocks gravitational waves. This may be how advanced civilizations communicate if they exist. If they've solved exotic matter, if they've built warp drives, which leads to an unsettling question. If warp travel is possible, why don't we see anyone? For decades, we've searched the sky. Radio telescopes listening for artificial signals. Optical surveys hunting megastructures. Gravitational wave observatories measuring cosmic tremors. And so far, nothing. No engineered radio bursts. No alien technology. No unmistakable signatures. Only silence. No signs of stellar engineering. No gravitational wave patterns matching anything resembling warp propulsion. Maybe exotic matter simply cannot exist, and no civilization, anywhere, has ever built a warp drive. Maybe intelligent species are out there, but use entirely different methods. Wormholes, higher dimensional shortcuts, physics we haven't even imagined yet. Maybe warp drives do exist just too far away for us to detect. Or maybe we're alone in this region of the galaxy. And then there's the darker possibility. Maybe civilizations that develop warp technology don't survive it. Maybe the destructive potential is simply too high. Maybe accidental particle beam events wipe out entire biospheres. Maybe instability failures erase their creators. Maybe warp drives act as a filter, a technological step that looks like progress, but ultimately prevents civilizations from ever spreading to the stars. We don't know. We're speculating about alien societies we've never encountered, using machines we cannot build. What we do know is this: if warp drives are possible, they are dangerous. They are not clean solutions to interstellar travel. They are double-edged technologies capable of opening the galaxy or destroying it. Your ship still orbits Proxima b. Radiation levels are slowly declining. Atmospheric chemistry is stabilizing, though likely altered forever. Whatever life once existed below is dying or already gone. You came as an explorer, a representative of humanity, a peaceful visitor. Instead, your arrival became an attack, unintentional but irreversible. And this is all assuming the drive could be built at all, assuming exotic matter exists, assuming every technical problem could somehow be solved. Maybe it's better that we can't. Maybe the door should remain closed. So step back. Come home from Proxima Centauri. Leave behind imagined warp bubbles, particle beams, impossible matter. Return to Earth. You're here now, beneath the same sky humans have looked up at for hundreds of thousands of years. Proxima Centauri is up there somewhere, invisible to the naked eye, too faint to see but real, 4 light-years away, along with hundreds of billions of other stars in our galaxy alone. You still can't reach them. You can't visit alien worlds. You can't shake hands with other forms of life if they exist. The cage remains locked, but something has changed. You now know there's a loophole. You know the speed limit isn't as absolute as it once seemed. You know space itself can move faster than light, and has been doing so since the universe began. It did during cosmic inflation. It does today at the edges of the observable universe, where galaxies recede faster than light. We didn't break the rules. We found the fine print. For a century, physicists believed faster-than-light travel was impossible. It belonged in science fiction, alongside time machines and magic. End of discussion. Then Alcubierre asked a different question. Not, can something move through space faster than light? But, can space itself move? And Einstein's own equations, the same equations that enforce the speed limit, answered yes. Objects are limited. Space is not. That realization matters. Maybe we never use it. Maybe exotic matter is fundamentally forbidden. Maybe quantum mechanics prevents it beyond microscopic scales. Maybe humanity is bound to this solar system forever. But we asked the question. We found the edge of what seems possible and pressed against it. That impulse is deeply human. We look at boundaries and ask, what if? We see cages and search for exits. Every impossible thing humanity has ever achieved began that way. In 1903, powered flight was considered fantasy. Humans had tried for thousands of years, wings, towers, gliders, all ending in failure. Everyone knew it couldn't be done. Then, the Wright brothers flew for 12 seconds, barely airborne. But they proved it was possible. 66 years later, within a single human lifetime, we walked on the moon. from 12 seconds of flight to leaving Earth entirely. That's the pattern. Impossible becomes difficult. Difficult becomes achievable. Achievable becomes routine. What one generation cannot imagine, the next takes for granted. Maybe warp drive follows that path. Maybe we're in the pre-Wright brothers era with equations instead of wings. We understand the concept. We know the requirements. We're identifying the obstacles. Maybe in 60 years there will be prototypes. Maybe someone born today will witness the first warp flight. Or maybe not. Maybe warp drives are truly different, like perpetual motion machines. Perfect on paper, impossible in reality. Something that collapses under deeper scrutiny because nature simply forbids it. We won't know until we try, until we search more thoroughly for exotic matter, until we complete a theory of quantum gravity, until we either find the solution or prove none exists. And even if we fail, the attempt still matters, because trying teaches us. Pushing boundaries expands knowledge. Often, when we search for one thing, we discover something else entirely. Fleming was trying to fight infection and discovered penicillin. Penzias and Wilson were eliminating noise from a radio antenna and found the cosmic microwave background, confirming the Big Bang. History is full of accidents born from curiosity. Maybe the search for exotic matter unlocks new quantum physics. Maybe optimizing warp equations reveals deeper truths about spacetime. Maybe we never build a warp drive, but uncover something equally profound. Or maybe we do build one. Maybe the breakthrough comes from a direction no one expects. Maybe dark energy turns out to be usable. Maybe string theory is right. Maybe some brilliant 20-year-old alive right now will have the insight that changes everything. We don't know. We can't know. The future is genuinely open, but we do know this. We are the species that found the loophole. The species that looked at the cosmic speed limit and discovered the exception. The species that mapped a route to the stars, even if we can't walk it yet. We are prisoners who found the blueprint for escape. The blueprint may require imaginary materials. The door may remain sealed forever. But finding it changed us. We are no longer prisoners who don't know they're trapped. We understand our limits. We know the size of the cage. We see its weak points. And that awareness, paired with refusal to accept confinement, is the engine of human progress. 70,000 years ago, early humans looked at the stars with nothing but wonder. They didn't know what stars were. No sense of distance, no grasp of scale, only awe. Now we know. We know stars are distant suns. We know some died long before humans existed. We know their light is ancient. We know galaxies hold hundreds of billions of stars. We know the universe contains trillions of galaxies. We moved from wonder to knowledge. And knowledge didn't diminish wonder. It magnified it. Knowing Proxima Centauri is 4 light-years away doesn't make it less astonishing. It makes it more so. Knowing we can't easily reach it doesn't stop us from trying. It makes us try harder. That is the human response to limitation. Not surrender, not resignation, but curiosity. And we are small, unimaginably small. Yet we keep looking up. Earth is a pale blue dot in a photograph taken from the edge of our own solar system. And for most of the Milky Way, our solar system is effectively invisible. Our galaxy is just one among trillions. We are small, temporary, fragile, a thin, delicate layer of thinking matter, clinging to a rock that orbits an average star in a galaxy that isn't special in any obvious way. And yet, we're also something else. We are the part of the universe that woke up, the part that became aware, that began asking questions, that started trying to understand what it is and why it behaves the way it does. We are the universe, looking back at itself, studying its own laws, testing its own boundaries, trying to read the fine print of reality. And in that fine print, we found something startling. A loophole, a door in the cage, a theoretical route to the stars. Maybe we walk through it. Maybe we never do. Maybe the door is permanently locked. Maybe we find different doors entirely. But either way, we do what humans always do. We search, we push, we refuse to accept limits without first seeing whether they're truly limits. That's what makes us human. Not winning, but striving. Not arriving, but moving. Not possessing all the answers, but learning how to ask better questions. Warp drive appeared not as a fantasy, but as a consequence of Einstein's equations. We may never build one. We may never touch exotic matter. We may never cross light years in days. But the concept exists. The math exists. We pushed physics to its edge and found something unexpected waiting there. We discovered that the cage isn't as absolute as it once seemed, and that gives us something rare. Not certainty, but possibility. Not escape, but hope. A map towards something extraordinary. Even if we never finish the journey, you're sitting here on Earth under stars you cannot touch. In a solar system you may never leave. Yet you now know the door exists. You know the speed limit has exceptions. You know the universe itself demonstrates faster than light behavior, not for ships, but for space. Space can outrun light. Space has been doing it since the beginning. Maybe we learn how, maybe we don't, but we are trying. And the trying, the refusal to accept impossibility without testing it, is one of the most human things we do. We are trapped in a beautiful cage. Windows that reveal a universe of 1 trillion galaxies. Bars made of physics itself. But we found the door, even if it's locked, even if the key is imaginary. We found it, and that alone is enough to keep the search alive. You're here now. On Earth, the same planet where humans evolved, built civilizations, and stared upward with wonder. The stars are still there, still unreachable, still absurdly distant. Proxima Centauri is still 4 light years away. Andromeda is still millions of light years out. The cage hasn't changed. But close your eyes for a moment. Imagine you're standing inside a spacecraft that doesn't exist yet and might never exist. The exotic matter systems are humming, powered by technology we don't have, fueled by materials we've never held. The bubble forms. Space tightens in front of you and stretches behind you. Inside the bubble, everything is normal. Your floor, your gravity, your breath, your heartbeat. You aren't moving through your local space at all. But that local space is moving. It's being carried. You're riding a wave of geometry itself. Stars smear past, not because you're accelerating, but because space is flowing around you faster than light can cross it. 4 light years in 36 hours. A journey that should take 70,000 years, compressed into a day and a half, not by breaking physics, but by exploiting its exception. Not by smashing the rules, but by persuading space itself to do the traveling. Then the bubble collapses. You arrive. Another star, another system, another world. 4 light years crossed. You look back toward Earth. It's just a pale yellow star now, among thousands, impossible to pick out without instruments. Home, 4 light-years away. But you cross that distance in the time it takes to live through a long weekend. You did something that feels impossible by using what was always possible, hidden in the universe's own wording. Open your eyes. You're still here, still on Earth, still inside the cage. Warp drive remains theoretical. Exotic matter remains questionable. The door is still locked, but now you know it exists. You know space can do outrageous things. You know the universe left a clue in Einstein's equations, a description not only of our confinement, but of a potential escape route. Maybe we never build it. Maybe exotic matter is prohibited by nature at a deep level. Maybe quantum mechanics will always crush large-scale negative energy. Maybe we're bound to this solar system forever, watching galaxies drift away beyond reach. Or maybe not. Maybe in 50 years someone makes a breakthrough, discovers a method for negative energy we never considered, figures out how to generate it, stabilize it, shape it. Maybe that person is already alive. Maybe they're a child right now, staring at the stars, wondering what's out there, and they'll be the one to turn the key. Maybe it takes a century, maybe 2. Maybe it never happens. The universe doesn't adjust its laws to match our patience. It doesn't care about our timelines. Either the ingredients exist or they don't. Either the door opens or it doesn't. But while the answer remains unknown, we can still imagine. We can still calculate. We can still press against the boundary. Out there, right now, space is expanding faster than light. Galaxies are being carried away on the tide of growing space-time. The universe performs the impossible casually, constantly, effortlessly. It has done so since inflation, when the universe grew from smaller than an atom to larger than a galaxy in a fraction of a second. Since the beginning, reality has shown that it knows how to sidestep its own speed limit. The universe keeps demonstrating it. We just don't yet know the trick. We don't yet know how to ask space to carry us, how to create those waves of compression and expansion on demand, rather than waiting for cosmic expansion to do it across the heavens. Maybe we learn, maybe we don't, but we found the equation that describes the mechanism. We mapped the route. We know what would be required, and now the task is to find it, or to prove it cannot exist. Until then, you're here under these stars, in this cage, with windows showing you everything you cannot reach. But you're also here as part of the species that found the door, that drew the map, that looked at an absolute limit and discovered an exception. You're trapped, but you're the kind of trapped creature that understands the trap, searches for exits, and refuses to stop asking, what if? Maybe that matters as much as escape itself. Maybe being the kind of mind that dreams of warp drives matters more than ever building one. Maybe consciousness, this awareness of limits paired with the imagination of going beyond them, is the real gift. You are small, absurdly small, a pale blue dot in an ocean without shore. But you are also the part of the universe that woke up, looked around, and began questioning its own nature. The universe studying itself. The universe attempting to outgrow its own boundaries. And you found a door. Even if it's locked. Even if the key is made of impossible matter. Even if you never open it, you found it. The stars are still unimaginably far. You still can't touch them. But you can imagine surfing space-time itself, riding waves of compressed and expanded geometry, crossing light years in hours, arriving before light can follow. You can imagine the impossible. And that imagination, that refusal to accept cages without questioning them, may be the most human thing we have. So rest now. Under stars you cannot reach. Inside a cage you cannot open. But dream of warp drives. Dream of exotic matter. Dream of the day we find the key or prove the key was always an illusion. Dream of sliding through the cosmos, of touching worlds no human has seen, of watching suns rise that no one from Earth has ever witnessed. Dream of the impossible, because we are the species that keeps turning impossible into real. One calculation at a time, one discovery at a time, one dream at a time. The universe left a clue, and we noticed it. Maybe we never reached the stars, but the fact that we found a way, even in theory, means we were never meant to stop trying. Good night, and dream of the stars.